Hello everyone, welcome to GIS Man. I'm Miles Lee. This video is to continue with the last video, which talk about a very useful FME design pattern called ETOR. If you didn't watch my previous video, the ETOR means a combination of workflows including the geometry extraction, geometry transforming, the spatial or attribute operations, and the geometry recovery. With the help of this design pattern, you can reduce lots of redundant FME transformers and make your workbench much simpler, and at the same time you can make your workbench runs much quicker in big datasets. So let's recap what we have done in the last video. So in the last video, we have a scenario of the clip traffic network. So in this traffic road network, we have some dual carriageway. The red polyline represents the prescribed direction, which don't have any traffic volume. And then the blue line represents the counter direction, which have some traffic volumes. And what we need to do in the last week's video is that we create a buffer from our prescribed direction and then intersect with our counter direction polyline. And then we will need to copy the value from the counter direction into our prescribed direction. And finally, we will need to recover our polygon geometry back to our original polyline geometry for the prescribed direction. So let's take a look at our workbench in the last video. Firstly, we read in our prescribed direction polyline and then extract its geometry and save it into a binary attribute. And after that, we will create a buffer for it, which turns the polyline into the polygon. And at the same time, our counter direction polyline will directly input into our supplier of the spatial relator. And our polygon will be as the requester. And we will use the intersects to relate them together and put our polyline, which is the counter direction, into the list. And after the output of the spatial relator, we will use the Python caller to copy the value, copy the traffic volume from the leaks item, which is our counter direction, into our prescribed direction. And now it's still a polygon because the outputs is as same as the requester's geometry shape. So what we need to do is to use the geometry replacer to recover it back to our original geometry, which is the polyline. Okay. So this is what we have done in last week. As what we can see, the ETOR design pattern makes the workflow very clear and simpler. If we don't use the ETOR design pattern, we will need to use the feature mergers to recover the geometry back to its original geometry shape. So let's get started of today's topic. Today we will do in another way. We don't create the buffer for our prescribed direction, and instead we will create a buffer from our counter directions. But we still use our prescribed polyline to intersect with the polygon, which is our counter direction, which means that we will put the polygon into the list. In the last video, you can see that we put the polyline into the list, but now we will need to put the polygon into the list. And then finally, we will need to export process and then explode the list and then recover the geometry of this explode list geometry. So let's get started to do that. So firstly, as usual, we will need to have the feature reader to read in our prescribed direction and counter direction polyline. I just copy and paste them from my previous video's work. Okay. And after this, what we are going to do is to create a buffer for our counter direction polyline. To do that, according to our ETOR design pattern, we will need to extract the geometry first and store it as an attribute. And after this, we can create a buffer for that. Okay. And then we will need to have some spatial relationships between our red polyline with the blue polygon. Okay, so what we are going to do is to use the spatial relator, and then the red polyline, which is the prescribed direction polyline, will be input directly as the requester. This is different to the last implementation. In the last implementation, we will transfer the prescribed direction polyline into the polygon first before using it as the requester, but now we directly use it as the requester. And then the transform geometry of the counter polyline, which is a polygon now, will be input as a supplier. So when we use the intersect, we will have the spatial relationships between these two geometry, and then we will create a list to store the polygon. Okay, so in the previous video, we take the polyline into the list, but this time we will take the polygon and push it into the list. Okay, so after this, we need to have some calculations. Because it's just as same as the previous video, I just copy and paste it. If you didn't watch my previous video, I can briefly talk about it right here. This is basically take the list items CWC ID, the carriageway code, and then take the requesters carriageway code, compare them if they are the real dual carriageway. If yes, then we will copy the value, which is the traffic volume from our list item, into our requesters traffic volume. Okay, and then output the feature. So by now, what we can see is we have the polyline P going into the requester. We have the polyline C going into a polygon C. Sorry for this. Polygon C going to our supplier, and then with the intersection relationship, we take this into the list. We push it and store it into our list. So the list now holds the polygon, and the prescribed polyline holds the list. Okay. I just make some notes right here to avoid the confusion. This is the polyline C. Okay. So after the Python caller, what we can see is still the polyline P geometry. Polyline P means the prescribed direction polyline. So because polyline P holds the list of the polygon C, so what we need to do is to use the list exploder to explode all the attributes item in the list, which is the polygon C's attributes item. Okay, so we just explode the obtain supplier list, and we only use the list attributes. And usually after the list exploder, we will remove the duplication, because when we do the spatial relator, it's usually one-to-many. Okay, and then we will use the unique ID to filter out the duplication. So after this, we can see here is the output is the polyline P with all explode attributes of the polyline C, which means that the geometry is still the polyline P, because the polyline P goes into the requester. Okay, but however the attributes is now becoming the polyline C's, because the polyline C's transform into the polygon C and then hidden in our list. Okay, now we explode the list, so we can see the attributes will be polyline C, but the geometry is still polyline P. And then we will use our ETOR design pattern to recover the geometry, back to our polyline C. Okay, because we saved the geometry previously, so now we can use this attribute, the binary, to recover the geometry back to the polyline C. So what we can see right here is before the geometry replacer is the polyline P with all explode attributes of polyline C. Okay, and after that, all the geometry has been transformed back into the polyline C. Okay, so right here, what we can see is we recover the geometry back to the polyline C. Okay, so now we got the output for the polyline C. We recover, no matter how complex in between what's the transformed geometry it becomes, now they are recovered and they are going back to the polyline C. And at the same time, we will also need to output the polyline P after the Python caller, because we have already got the value from the polyline C by the Python caller, so we can directly output it. Okay, so I think everything should be fine here, and let's run and take a look how it goes. Whew. So let's refresh our folder and take a look at the results. In our results, what we can see is, you see, now the prescribed direction has already got the value. You can also check other dual carriage rate. So now both the prescribed direction and counter direction polyline have got the value, and at the same time the polygon buffer of the counter direction polyline has been recovered and go back to the original polyline. So That's all for this ETOR design pattern. The advantage of the ETOR design pattern is no matter how complex in between what geometry change, at the end of the day, we can recover it back to its original geometry for other using purpose. Actually, I use this design pattern in my projects quite often. I can show you some of it. For example, this is my project, the view project, and you can see the workbench, the logic is quite complex. And for example, right here, I extract the geometry from the previous step and then use a line combiner, which is some spatial operation, and then come with a Python caller, which is some attribute operations. Okay, and then do lots of stuffs, even do the explode and aggregate again based on different parameters. But finally, we go into the geometry replacer, which help the streams, help the geometry to be recovered back to its original geometry for other use later. Okay, I use these kinds of techniques quite often. Even just in one workbench, I use it many places. Like right here again, we have a geometry extractor and then line combiner, Python caller, and then finally we'll use the geometry replacer to get it back to its original shape. So this technique is very useful and can simplify your workbench. Without the help of this design pattern, I think my workbench will be larger and more complex, and it's not good for maintenance. So that's it for today. If you have any idea or if you don't understand some points, you could leave the message below and I will respond to you. And thank you very much for your watching, and stay tuned and see you next time. Bye.